Hello and welcome to this new video where we discuss mathematics and physics on the board. In this video we are going to touch on something that usually is not well appreciated and in fact maybe detested by students and sometimes by lecturers as well and teachers. It's basically the concept of free energy. There are plenty of different ways of going about this, and in this video we are going to see one of them, which I hope you're going to find insightful. Okay, so as usual, let's set the stage of what we are going to talk about. So, first of all, I'm going to mention the second law of thermodynamics. And in fact, it comes as a package of two things that are in fact completely different. The first one is that there is a quantity called entropy, which in principle you can ascribe to almost any object you can think of, out there. And basically the way people are going to formulate it nowadays is that the variation of the entropy of the entirety of the universe has to be larger than zero, or equal to zero. Okay, so it has to increase, so the entropy of the universe has to increase or remain the same. That's how people would say it. So that's the sort of qualitative feature associated to the second law. And then there is a quantitative feature or property, which was stated by Clausius, and basically says that the elementary variation of the entropy of the system is going to be equal to the heat received by that system divided by the temperature of that system. And if you remember, and I'm going to put it somewhere, I've already flagged how this could be constructed as a mathematical problem to define an integrable quantity from a non-integrable one, which is delta Q. And T was associated to a problem that is called the Pfaffian problem. So you can look at this video if you want, but basically this is just to say that this is how this is also stated from experimental insight as well. So once we have said that for the second law, then we can move on to the first law. And I'm going to focus here on closed systems. You can go back to some of my previous videos and discussions where I actually mentioned that the laws of thermodynamics are quite complicated to pin down, precisely because, in fact, nobody has actually pinned down, themselves. That has proposed a framework with which everyone was going to be happy, and so there are almost as many ways of stating the first and second laws, and even adding some more on top of that. As there are people teaching the subject and perhaps even people doing the subject. So I'm not going to be nitpicky here. I'm just saying, let's assume we are in a closed system. So the amount of matter is fixed in the system, including the composition of the system. And then I simply say that delta U, the variation in internal energy in that system, is going to be simply W plus Q, where W is a work received by the system and Q is a heat received by the system. Now, sometimes you may see in some textbooks minus W plus Q. That's because there is a sort of mixture of convention. Here, I'm in a fully so-called receiver convention where both W and Q correspond to received energy. Okay, so by the system. So if, for example, W is positive, that means that the system has received energy that is kind of positive. If W is negative, that means that the system has kind of emitted and lost energy into its environment. Okay? So now let's actually go towards what it is that we want to look at in the context of the Helmholtz free energy. So, and the logic is the same afterwards. So if you want, you can try to try other stuff with other free energies you're aware of. So let's assume that you're in a situation where you know that there are experimental constraints, And so you say that there are known experimental constraints. And these experimental constraints are going to be fixed temperature. By the way, I forgot to mention, but here the T is to be expressed in Kelvin, okay? And in fact, that's, again, in the video I showed for the Carat-Theodori axiomatic version of temperature and entropy, T here is the function that represents basically this notion of absolute temperature, which is itself a function of the experimental temperature, and only that. It's not a function of anything else but the experimental temperature. And that's kind of the beauty of the work of Carat-Theodori. Anyway, so move on. So T here is the absolute temperature, and we assume that to be fixed. Which means that the experimental temperature is fixed, that nothing else, and volume. And we already said that we had a closed system, so the number of particles is fixed as well, and volume. Okay, so that's the first thing. So we know that we've got some experimental constraints. Now, what I'm going to do is what people do or want to do usually is that they assume that there are macroscopic controllable thermodynamic variables, and that's going to be temperature, volume, that can be things related to pressure, maybe energy in some cases, and so on. And then from that, you want to know in which direction, if you will, or how the things are going to evolve over time upon applying this particular second law principle, so that the entropy of the universe need to increase or remains the same. Now, it's a bit cumbersome to, if you look at a single system, let's say a cup of tea or something, to somehow try to imagine what's happening everywhere in the rest of the universe, etc. And essentially, the notion of free energy is precisely aimed at discarding the environment and somehow looking only at a single quantity, that function that is only a function of state of the system itself. So, so how does that work? So basically what we start to do is that we split things. So we say that the delta S of the universe is going to be delta S of the system, and then plus delta S of the environment. Okay, so then if I apply the second law, I've got that delta S of the universe is equal to delta S of the system plus delta S of the environment, and that's actually larger than or equal to 0. Now, this is general, that can be used whatever the case. Now, what's going to be specific is now we need to work, and that's the only thing, we need to work on delta S environments, and that's it. So our basically objective here is to find out an expression of delta S environment that is going to involve only quantities that are about the system itself. So you've got simply a system, and you imagine the rest of the universe, and then somehow you say, well, my system is interacting with the rest of the universe in some form, and then how is that going to affect this quantity? So let's see. So if I apply the fact that the temperature of my system is actually constant, then in a sense it means as well that the temperature of the environment has to be constant if I assume any exchange of heat, for example, happening between the two. So if I assume the exchange of heat not being 0, then I'm compelled and obliged, in fact, to say that the temperature of the environment is the same as the temperature of the system. But therefore, what I mean is that I'm going here to write from this equation, this is Q of the environment divided by T of the environment. And here I've used the fact that the temperature of the environment was essentially considered constant in that particular situation, and that can be, in that case, also justified by that. Usually, the temperature of the environment anyway tends to be considered uniform, because it's considered to be imagined as a series of thermostats, for example. So this, you're going to get that, but then, the heat that is received by the environment, if the only thing you have in your universe is a system and its environment, then the only place the heat received by the system can go, received by the environment can go or can come from, is from the system itself. So it's something additional to basically the first law. It has simply to do with where does the heat come from. So if you've got a source of heat, it's not like the heat is going to be created ab nihilo in this particular case, because we are not in a context where we are in a closed system, so we are not, for example, expecting any kind of chemical reactions going on, where the species change throughout the system and so on. So here we've got Q environment, and basically this is going to be equal to minus Q of the system divided by T of the system. And here is just because I've assumed that the temperature of the environment was equal to the temperature of the system, and then that the heat received by the environment was coming from the system itself. Okay? And again, I did not assume that there was any internal heat coming from the environment, within the environment. Okay? Now, that could be addressed, but that's not something I'm going to put here. So then what we do is we apply the first law. So I say, well, Q system is equal to delta U minus W. So I've got this is delta U system minus W system, and then divided by T system. Okay? And then, so I'm almost there. Basically here I'm saying, well, constant volume in most system, constant volume is going to entail that the work received by the system is zero. Okay, because usually the work is done by expanding or shrinking the size of the system. So W here is going to be zero. And so upon replacing here, I'm going to get that delta S system, and then plus delta S environment, which is minus delta U system divided by T system, has to be larger than or equal to zero. Now what I do is I multiply the whole thing by minus T system, and I end up with basically that I need to look at delta of U of the system minus T system, S of the system, and then this being zero, less than or equal to zero. So this quantity here is what we call A, and that's the Helmholtz free energy. Okay? And essentially what this thing is telling you is by looking at properties and functions of the system itself, basically, what are the transformations which are going to obey that particular equation? That these are transformations upon which delta A is going to be negative and or equal to zero. And all of these are going to be permitted thermodynamical transformations or evolutions. And anything that does not satisfy that won't be permitted. And again, permitted by what? Permitted by the second law of thermodynamics. So the thing here is that the goal, at least one of the goals of the free energy, is actually to tell you in which direction the system is actually evolving. Or, again, said differently, because that's more the way it's done, is more upon looking at various kinds of transformations, basically we can select those that are going to basically be favored by the second law and rejected by the second law as well. Okay, so that's kind of the idea. And again, we only need to compute quantities that are about the system itself without caring about the environment as well. So it's kind of all done in one go. Okay. So basically, that's it. If you've got any questions or comments about this, by all means, do let me know in the comment section. And otherwise, see you in the next video.